As first objective, you'll be able to find the derivative of a function using the limit definition. Let's take a minute to look at the image that's here. It just looks like part of a graph, right? Or the whole entire graph, something to do with some sort of graphs. But I think that you might recognize the purple thing that's in this image. What you are missing, though, is like usually there's an x-axis that goes right through here, and usually there's like a y-axis that would go right through. Actually, it would go. I'm gonna say it's right through here. Go away! Go away! Go away! Get off my screen. Y-axis right through there. What's that purple thing? That purple thing is tangent. Is y is equal to tangent. I wonder what the green thing is. It's curious. We won't find out for a while, so I'm just going to keep you in suspense. So here then is the definition of the derivative. Not derivative at a point, but the derivative written as a function, so it's the derivative everywhere. The derivative of f at x is given by, it's going to be a limit. I bet it's going to be a limit. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Now notice that this looks just like the derivative at a point, but it uses x and it keeps x in there, and when we're all done, we're going to get a function, provided this limit actually exists. For all x for which this limit exists, f prime, that's how I read that, f prime is a function of x. Momentarily, part of this lesson, we will find a whole bunch of different notations for the derivative, but this is the first one, and I just read it as f prime. I know it's a derivative of the function, and what does derivative give me again? It gives me the slope of the graph at a particular point, and if I write it as a function, it's giving me the slope of the graph at every single point. And if it's a function, doesn't that mean we can graph it? We can graph it as like x and y coordinates? Absolutely. Look at example 1. Explain what is meant by f prime of 3 is equal to negative 1. So we have an input value of 3, and then the output is negative 1. This is a derivative, and the derivative gives me a negative 1, and remember, derivative means slope. So really, this means at x equals 3 on the original graph, the slope is negative 1. Okay? And like going a little bit deeper, anything that we choose to plug in here, that's part of the domain, right? So this is the set of all numbers for which you can actually take the derivative of your original function. It's not exactly always the same thing as the original domain. The original function, it's a subset of it. And what that simply means is that, hey, just because your function's defined here doesn't mean you can necessarily take the derivative there. That's what our second objective is going to be about, where we can look at a graph and go, oh yeah, that's right, right here at this point, you can't take the derivative there. All right, our output values, our whole entire range, what we found here was a slope. It's going to be the collection of all the slopes at all those x values. Right? So the range is a set of all the slopes at each and every single one of those x values. Let's look at example 2, at least briefly, because I'm going to have you guys figure this out on your own. Use the graph of f of x at the right to draw the graph of f prime of x. So I want you, well, remember we said that the derivative is actually a function. I want you to graph that function given that this is the original function. In other words, what we're going to do is we're going to draw a picture of the slope of every single one of these points, and it's going to make another function. To help you out, take a look at where the slope is equal to 0. The slope is equal to 0 at each one of these minimum and maximum points here, which means that whenever we draw the graph of the derivative, it has to hit the x-axis right there, right? It's got to hit the x-axis here at, looks like a half. It's got to hit this x-axis here at 2. It's got to hit the x-axis here at 4. But what's it going to do in between those two things? So something else to think about is, let's look at the left side of this graph, on the left side of a half. Notice that the graph is going down. It's like decreasing. What does that tell you about the slopes? What kind of numbers are the slopes there? And then on the right-hand side, it's going upwards. It's increasing. What does that tell you about the slopes in between half and 2? All right, so that's going to conclude this video, but before you start the next one, I want you to try to draw the graph of the derivative of this particular function.